So one of the first things you learn to graph in algebra is a line. And we're going to continue along that same idea, but we're going to be looking at not linear equations, but linear inequalities, and we'll look at those in 2 dimensions. So we'll start with a very basic example. Let's say I want to graph the inequality x is greater than or equal to -1, and we want to graph it in 2 dimensions. Let's say this is one-dimensional because there's one variable, okay? One variable. And it's linear because that variable is to the first power. So we know in 2 dimensions it's going to be a straight line. So in 1 dimension, let me just mention, if you did graph this in 1 dimension because there's only one variable, what you could do, what you would do is you would create a one-dimensional number line, right? A line is 1 dimension. So you would graph a single number line. You would call it the x number line, right? You'd call it the x number line because the variable in this 1 dimension is x. And you'd mark -1 somewhere on that number line. So this is the x value of -1. And you'd want to graph everything equal to or bigger than -1. So anything equal to it, you would shade. So that would be a shaded circle on -1, or a closed circle is often said. And then you would shade everything bigger also. And so all of these x values are equal to -1 or bigger. So that's if you were graphing in 1 dimension. But we want to graph this guy, in 2 dimensions. In 2 dimensions, okay? So this is 1 dimension here. But this will help us understand the 2-dimensional graph. When you graph this in 1 dimension, you basically get half of the number line shaded. When you graph it in 2 dimensions, that number line turns into a plane because it has a horizontal number line and a vertical number line. And specifically, the horizontal is called the x-axis and the vertical is called the y-axis. Now, what this means is if I want to graph this guy, I want to graph all the solutions to this inequality. In 2 dimensions, I'm looking for ordered pairs, all of the ordered pairs that make this statement, x is greater than or equal to -1, that make that statement true, okay? So for example, an ordered pair, let's say -1, 5. This ordered pair makes this true because the x value equals -1 and -1 is greater than or equal to -1. In fact, any ordered pair with an x value of -1 will make it true because x can equal -1. But if I pick an x value bigger than -1, that will also make it true. So I could choose 0, anything. I could choose 1, anything, etc. There's a lot of ordered pairs. I could choose -0.753 with the 5, 3 repeating, anything, and that would also make it true. There's so many ordered pairs. How can we represent all of them at once? And the best way to do that is with a graph of the solution set to this inequality. So when we say we're graphing the inequality, we're really graphing the solution set. So that may be how it's phrased in some places. So how do we graph all of those ordered pairs? Well, it's very similar to the 1-dimensional graph, except that instead of this boundary point, you can see the shading stops at a single point here. In 2 dimensions, we have what's called a boundary line. So the boundary line here is the same inequality but turned into an equation. So the boundary line is x equals -1. So let's locate where x equals -1. Every point where x is -1 lives on this line. This is our boundary line now. This is the boundary line x equals -1. It's a vertical line that crosses the x-axis at -1. Okay, so that's our boundary. That's similar to this boundary point in one dimension. Now we have to shade. We have to shade every x value greater than or equal to -1, okay? Greater than or equal to -1. So one way to think of it is, okay, if it equals -1, it's on this boundary line. So I'm going to shade this whole line now, understanding that my label here is -1. That's the boundary, just like the point was shaded over here. And then I need to shade all the x values, all the points with x values bigger than -1. Now here, instead of being just on the x-axis, it's actually everything in the plane to the right of that boundary. So it's like taking the one-dimensional solution and then stretching it vertically to change it into 2 dimensions. And so what we get here, what this is we've taken our plane, right, our 2-dimensional plane, we cut it in half with our boundary line and we shaded half of it. This solution is called a half plane. And when you solve these or graph these inequalities in 2 dimensions, you get a half plane. Just like in 1 dimension, you would get half of a line, okay? So that's a great example. How did we do it again? We took the inequality, we turned it into a boundary line with an equals. We graphed the boundary line, and then we shaded to the right here. And that's because x could be greater than -1. So that means go to the right. Okay, so that's a simple example to get us started. Let's look at another basic example that's similar, but we'll use the variable y instead. All right, so the next one is to graph y is less than -2, and we want to do that in 2 dimensions. So now we could do it in 1 dimension because it's one variable, but we want to do it in 2 dimensions. We're going to jump right to the 2-dimensional case. So let's set up our plane. This is our x-axis and our y-axis. And the first thing we need to do is graph the boundary line. The boundary line is y equals -2. Now we have to be careful here because in this case, y has to be less than -2. It can't actually equal -2. So I don't include my boundary line as part of my graph, okay, as part of my solution. So the way we can indicate that we have a boundary that's not actually part of the answer is don't make it a solid line, make it a dashed line or a dotted line. So y equals -2 y equals -2 crosses the y-axis at -2. And so it's this horizontal line, and we make it a dashed line now. We have a dashed boundary line. I always recommend labeling the equation of your boundary line. Your boundary line is always an equation because lines are equations, okay? So that's the boundary of the half plane that we're going to shade, right? This is an inequality. When we graph it, it's going to be a half plane. Here's our boundary. This is the guy that cuts the plane in half. That boundary is not actually part of our answer, but now we decide, okay, do we shade the top half or the bottom half? And this one's really simple. Because y is less than -2, we have y is less than, that means we shade, remember y means you measure up and down with y. If y is less than, then that means we shade below the boundary line, okay? Shade below the boundary line. So all of the ordered pairs in this half plane on this side of the boundary line make this inequality true. And you can see that pretty easily. You could test a couple points here. Let's test the ordered pair 0, 0 in the inequality y is less than -2, right? The point 0, 0 is right here at the origin. It's not shaded. That means it should not be a solution. So if I plug in 0 for x, well, there is no 0, right? So I don't plug that in at all. 0 for y, I get 0 is less than -2. That's false. And that our graph tells us that because we did not shade that ordered pair, so it should make it false. If we test another point, maybe in the region that is shaded, let's try maybe 4, -5, right? That would be a point that's shaded in our inequality. Then, well, there's no x again, so I don't really plug the 4 in anywhere. I just plug the -5 in for y, and I get -5 is less than -2. That's true. And it should be because that point for -5 is down here in our shaded region, our shaded half plane, okay? So this test point idea is going to be something that's going to prove pretty useful to us whenever we actually get inequalities that have two variables. Whenever these boundary lines start to slant, then this test point idea can help us out. So let's move on to something like that. And I'll show you two different ways to graph these when your boundary line slants, and then you can decide what you like the best. All right, so now we want to graph y is less than or equal to 2x minus 3. And I don't have to say in 2 dimensions anymore because there's 2 variables. So that's the natural way to graph the solution set, is with x and y, with 2 dimensions. This is going to be a slanted line though, so we got to keep that in mind. There's our plane. So our boundary line, we have to graph it first, just like before, is y equals 2x minus 3. And since this says y is less than or equal to, that means that our equals case is included in our answer. So we need to include this in our answer. So it's a solid line. And again, because that's because this has an equals. It could be less than or equal to. And the way to graph this is your mx plus b, right? This is your mx plus b. And so let's go ahead and plot it out. The y-intercept is -3. So there's -3. We could plot that point. And our slope is 2 over 1. So I'll rise 2 and run 1. And our graph roughly looks something like this. And it's a solid line, not a dashed line, as I said. So our boundary line is y equals 2x minus 3. So we've just cut our xy plane in half. We've just sliced right through it. We just have to decide which way to shade, okay? Now this is where I'm going to show you a couple different ways to decide. What I like to do is use a test point, just like we talked about in the last example. And my favorite test point is 0, 0, because it's so easy to plug in. Test 0, 0, and we want to test it in the original inequality. So if I plug in 0 in for x, I get 2 times 0 minus 3. If I plug in 0 in for y, then I get 0 is less than or equal to 2 times 0 minus 3. So what I want to know is if that's true. So the left side is 0, and if I simplify the right side, I get -3. Is 0 less than or equal to -3? It is not. This is false. What that means is that the origin should not, I'll put a red X there, the origin should not be part of our solution set, which means that we only have one choice. It means that we have to shade on the other side of the boundary line. So this side of the boundary makes up our half plane, okay? Now, another way to do it, since this happens to be in slope-intercept form, is, all right, we've got the boundary line. We can see that y is less than or equal to. That means shade below, just like we saw before. So if this is my boundary line and I want to shade below, that means shade this way. So that means I'd shade everything on this side of the boundary line, and we get the same solution set either way. So you can decide if you prefer to use a test point to decide which region to shade, or if you prefer to use the slope-intercept form and then decide if you shade above or below based on whether y is less than or y is greater than. Okay? If y is greater than, you'd shade above the boundary line. So let's do a couple more examples, and we'll do both of the examples both ways. Test point and slope-intercept form. Okay, so let's graph, and remember what we're really doing is graphing the solution set, but it's often described as graph 4x minus 8y is greater than 24. So now, this is not in slope-intercept form, and you don't have to put it in slope-intercept form either. I'll do it that way in a second, but because it's not in slope-intercept form, the easiest thing to do is when you look at your boundary line, our boundary line is made up of the equation 4x minus 8y equals 24. And this is what we call standard form when the x and y terms are over here and all the numbers are whole numbers or integers. Then we can graph the line using 2 points. And intercepts are the easiest. So what we could do here is we could plug 0 in for x. So if x is 0, this term goes away, and we have negative 8 times y equals 24. So if we divide by negative 8, write this out if you need to, if we divide by negative 8, we can see that y is negative 3. So that's the y-intercept. The other way around, we could plug 0 in, so I'll underline the negative 3 because we figured that out. The other way around is plug 0 in for y, which makes this term go away. And if we divide both sides by 4, we can see that x is 6. And now we have 2 points on our boundary line. 0, negative 3 is down here. 6, 0, 1, 2, 3, 4, 5, 6 is there. And because this does not have an equals in it, we don't include the equals case. So our boundary line is not included. Again, because the original inequality does not have an equals. So that means it's a dashed boundary line or a dotted boundary line. So when I connect these, I'm going to be careful to use dots instead of a solid line. Okay, so there's my boundary line. I'll go ahead and label it with its equation. That is really good practice. I know you're going to want to skip that part, but I kind of insist that you do it because eventually you get to systems of lots of these half planes, and it can become a big mess if you don't label all the different lines you can see. So get in the habit now. All right, so we've just sliced through our plane. We've got it cut in half. We just have to decide which region to shade. So again, you can use any test point you want, but my favorite is 0, 0. I think it's the easiest to test. So let's test 0, 0 in this inequality. 4x minus 8y is greater than 24. If I plug in 0 for x and 0 for y, everything on the left turns into 0 and says 0 is greater than 24. That's false. So that means I'm going to come to my origin, my 0, 0, and say that's not part of my answer as an indicator for that side not being shaded. So I have to shade the other side. Okay? All right, so this half plane is the solution set to this inequality. Now, how else could you do it? I'll show you another way. And I'll leave the graph here because you'll get the same answer. Another way to do it is to put your inequality in slope-intercept form. So what we'll do, and actually, let's go ahead and erase this because the equation is going to change when it's in slope-intercept form. It will look different, but still be equivalent. So we take 4x, so this is our boundary line, 4x minus 8y equals 24. You know what, I'm sorry, let's not call it a boundary line. We're going to focus on changing the inequality. So this is still greater than, okay? So what you do to get it in slope-intercept form is get y by itself. So let's subtract 4x over. So a negative 4x and still the positive 24. We divide both sides by negative 8. Now here's the tricky part. When you divide by a negative, this greater than flips. When you multiply or divide both sides of an inequality, something with a less than or greater than, when you multiply or divide both sides by a negative, that guy points the other direction. And that's why I prefer the test point method, because most students forget about this. So negative 4 divided by negative 8 is positive 1/2. And positive 24 divided by negative 8 is negative 3. And so here we have our boundary, or our new inequality, and we can get our boundary line, which is y equals 1/2 x minus 3. So if you look at 1/2 x minus 3, it's exactly the same as the boundary line we had before. Y-intercept of negative 3, rise 1, run 2. Rise 1, run 2. Rise 1, run 2. It has the right slope of 1/2 also. So now when I label it, I label my boundary line as y equals 1/2 x minus 3. It's the same line. And then the way that I know to shade below, is because when it's in slope-intercept form, it says y is less than, and when y is less than, you shade below, okay? So that's the slope-intercept form version of graphing the same inequality. Again, I prefer the test point method, but that certainly doesn't mean that you have to. That's why I'm showing you both ways. All right, let's do one more. And this time, we'll look at another one in standard form, but we'll do it by slope-intercept first, okay? Just so you can see how to do it from scratch. All right, so the next one is negative 3y minus 5x is less than 9. So this guy now, if we're going to do the slope-intercept version, we need to get y by itself. So I'm going to take it, I'm going to add my 5x to both sides. And then I'll divide both sides by negative 3. Since I'm dividing by negative, the symbol flips. So it turns into y, this turns into negative 5/3 x, and this turns into minus 3. I just divided both of those by negative 3. And then this guy, let's even use a different color. This guy changes to a greater than here. If I divided by positive 3, I wouldn't have a problem. This would stay where it is. But there we go. Now we can graph our boundary line, which is y equals negative 5/3 x minus 3. Boy, seems like I really like a y-intercept of negative 3, doesn't it? Apparently I do and didn't realize it. So there's our y-intercept. Then we rise negative 5 and run 3. So I go down 1, 2, 3, 4, 5 and run 1, 2, 3. So I've got another point there using my slope. I could also go the other way where I rise 5, 1, 2, 3, 4, 5 and run negative 3, 1, 2, 3. Anyway, there's my boundary line. Since there's no equals, it's going to be a dashed boundary line. So that boundary line is y equals negative 5/3 x minus 3. And because y is greater than, that means shade above. So above means go that way. So this region here will be the half plane. Every ordered pair in this half of the plane makes that inequality true. So that's how to do it using slope-intercept. Not difficult. You just have to be a little careful with remembering to flip that inequality symbol in some cases. Now let's do it using the standard form, okay? So I'll show you that. You'll get the same answer, so I'm not going to erase it. But the standard form, we look at the boundary line, which is negative 3y minus 5x equals 9. And since the original inequality does not include the equals, we know that this is going to be a dashed line. It's not included in our answer. Okay, so we've already got a dashed line. Now, how do you graph this? Well, it's in standard form, so intercepts will be easiest. So we'll plug in 0 for x to get y. We'll plug in 0 for y to get x. So if I plug in 0 for x, I can see that if I divide by -3, 9 divided by -3 gives me -3. So my y-intercept is still 0, -3, which we already knew from before. My x-intercept means plug 0 in for y. So if I plug in 0 for y, I would have to divide by -5. So my x value is -9/5, which is the same thing as -1.8. Okay? So apparently this point right here, here's -1, here's -2, -1.8 is between those. So we've got the two intercepts now instead of using the slope like we do the slope-intercept form. But I still get the same line, I just label it with a different equation. -3y minus 5x equals 9 is my boundary. And then how do we test where to shade? Well, we can't look at this and say y is greater than or y is less than to decide. We have to use the test point. Again, use any ordered pair you want. I'm going to go for trusty old 0, 0. And I'm going to test it in this inequality that we started with. So if I plug in 0 and 0 for x and y, everything on the left turns to 0, and 0 is less than 9 is true. So that means I am going to include the origin, which means that I need to shade the origin side, the 0, 0 side, and not the other side. Okay, so there's an example where 0, 0 does make it true, so that means shade on that side of the line. All right, there are many examples there on graphing linear inequalities in 2 dimensions. They're not too bad. Take your pick. I think it's best to know both techniques. If your inequality is in slope-intercept form, go with that. If it's not, if it's in standard form, go with intercepts. If it's not in either form, you can adapt. You can write it in slope-intercept form or standard form or whatever you want to do. Okay, but make sure you get your boundary line dashed or solid, shade the right side to get your half plane. Most students forget to shade. So practice and have some fun.